Hello, this is Jack Jackson. In this video, we're going to look at a couple of exercises, actually 4 exercises, where we go to and from or between definite integral notation and the limit of a sum notation. So we'll basically do 2 exercises in each direction. So the first 2 exercises, we're going to go in the direction where we're given a definite integral. And we want to rewrite this as a limit of a sum using the definition of the definite integral that we've been using in this class. So let's see if you can apply what we've learned to this particular problem here. So what we have is the integral from 1 to 11 of sine of pi x dx. So the idea is, can you rewrite this integral by using the definition as the limit of a sum? Okay, actually is the limit of a sum of what's actually is the limit of a right Riemann sum is the way that we've been doing this in class. Okay, so see if you can do it that way and work it out. Okay, try it on your own and then come back and check your work here in just a minute. Press pause now. Okay, well, the first thing we need to do is we need to define or find out what is delta x. Now remember, delta x is b minus a over n. And of course, a is 1, b is 11. A is the bottom number on the integral sign, and the bottom limit, we call that. And the upper limit, or right limit, is the one on the top, 11. So that's a b. So b minus a then is 11 minus 1, which is 10. So delta x is 10 over n. Now, to get it at the right end of each interval, we need to write down what x sub k is. X sub k is a plus k delta x. But we know that delta x now is 10 over n, and a is 1. So x sub k is 1 plus 10k over n. Now we just rewrite this. We know that the integral in general, the integral from a to b of f of x dx is defined to be the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k delta x, where delta x is b minus a over n and x sub k is a plus k delta x. So now just substitute in what we know. The function is sine of pi x sub k, so f of x sub k is sine of pi x sub k. So that limit is what we have. Now let's go a step further. Delta x, remember, is 10 over n, so we can put that out front. And we can go another step further. X sub k is 1 plus 10k over n, so I can replace the x sub k by parentheses, in parentheses there, 1 plus 10k over n. And I can replace the delta x by 10 over n. And so this sum is what's meant by this definite integral. By definition, this definite integral means this limit of this sum. It's just another way of writing this expression here. Okay? So we're doing nothing more than just using the definition and just kind of working out what some of the pieces are and substituting them in. So when we get done, we won't actually have a delta x or an x sub k in the final answer, but we will have some k's and some n's and some other stuff in there based on what we started with. Okay, so let's try it. Let's do exactly the same thing with a new function, a new definite integral. All right, so our new example is this one. See if you can do this one yourself. It's the integral from negative 2 to 12 of e to the power 5 square root of x dx. Okay, see if you can also take this one and rewrite it as the limit of a sum. Don't worry about trying to evaluate the integral. Just rewrite it in that different form. That's what it means by the definition. See if you can do that on your own and come back when you're ready. Press pause now. Okay. Well, once again, delta x is b minus a over n. This time b is 12, a is negative 2. 12 minus negative 2 is 12 plus 2, which is 14. Of course, you still have your over n, so it's 14 over n for delta x. Okay, and what is x sub k? Well, if we go to the right end of each interval, which is how we do in the basic definition we've been using, which is what we do for a right Riemann sum, x sub k is a plus k delta x. But let's substitute in what we know. A is negative 2, and we know that delta x is 14 over n. When you multiply k times delta x, that's 14k over n. Okay, continuing on. In general, the definition says the integral from a to b of f of x dx is defined to be the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k delta x. Rewriting that as a sum, substituting in now, x sub, let's see, f of x sub k is e to the 5 square root of x. So just wherever there's an x, put an x sub k. So it's e to the power of 5 times the square root of x sub k, and then we still have our delta x. So just replaced this function here, f of x sub k, as taking the original thing that's right here, sometimes that's called the integrand, the e to the 5 square root of x, and just put the x sub k in place of the x. So that's one way to write the sum, but we can go a bit further. Delta x now is, again, 14 over n, so we can replace delta x by 14 over n. And x sub k is negative 2 plus 14k over n, which can replace the x sub k right there. Now, at this point, we have our final answer, which is only an expression that's only in terms of n and k. Everything else is a constant. Okay. Hopefully you can see how that works. Now what we're going to do now for the next two problems is we're going to reverse it. I'm going to give you basically what we have as the answer here, and you're going to go back and find out how to rewrite it as an integral. And in fact, these next two, the shapes that we end up with are simple enough that we're going to find the areas using geometry. So as you know, the integral, especially if it's above the x-axis for the function, is just simply an area. In general, it's a signed area. Okay, signed net area, I guess I should say. But if the function's above the x-axis, it's just an area between that function, that curve, and the x-axis over some appropriate interval. So, in the next set of problems, what I'd like you to do is I'll give you an expression that'll look kind of like the answer from before. It'll be a limit of a sum. And you want to be able to figure out how you could rewrite that as an integral. And then since you know that an integral represents an area, you should be able to actually find that integral by finding the area using some formulas from basic geometry. Okay, here's your first example. All right. The limit as n goes to infinity of the sum from k equals 1 to n of, parentheses, 6 minus absolute value of 3 halves times parentheses 4 plus 8k over n, close parentheses, minus 12, close absolute value, close parentheses, times 8 over n. Well, that looks like a mess, doesn't it? Okay, so just take it a piece at a time and see if you can figure out how to get that into the form that we can recognize it as an integral. Okay, so the first thing is to notice it at least has the same basic form that we want for an integral, at least in terms of the outermost structure. It is a sum from k equals 1 to n of something, and then we take the limit as n goes to infinity. That's good news. This something should be f of x sub k times delta x. Now remember, delta x is going to be of the form some constant over n. So delta x is b minus a over n, and so we need some constant over n as a factor. Can we see that up here? Yeah, see this 8 over n? That must be our b minus a over n. So that means 8 is the b minus a. Now what we don't know yet is what the limits of the integral are, but we do know that they're 8 from the lower limit to the top limit. That b minus a is 8. So we're integrating over an interval of length 8. We just don't know where it starts and where it ends yet. Now, what else are we looking for? We're looking for x sub k. Now x sub k is a plus k times delta x. Okay, right here. X sub k is a times k plus k times delta x. But delta x is 8 over n, we've decided. So we're looking at, of course, 8 over n times k is 8k over n. So we're looking at something that is some constant plus 8k over n, where we have it substituted in here. Can you see anything that might work there? Well, hopefully you recognize that, hey, here inside this parentheses we have 4 plus 8k over n. Well, that might indicate that that was a plus 8k over n. If we do that, then a has to be what? 4. And of course b minus a equals 8. So b minus 4 equals 8, b equals 12. Or in other words, b equals a n plus n times delta x. And the n's cancel, you get 4 plus 8 is 12. So a couple different ways to look at that to see what b is. So b is 12. So we know, hopefully, that this is going to be the integral from 4 to 12 of f of x dx for some appropriate f. Okay, so here's what we have. Originally, we have the limit as n goes to infinity of the sum from k equals 1 to n of parentheses 6 minus absolute value of 3 halves times parentheses 4 plus 8k over n, close parentheses, minus 12, close absolute value, close parentheses, times 8 over n. Now the 8 over n in red here you can see is replaced by delta x, and the 4 plus 8k over n is replaced by x sub k. Well, now this is exactly the right formula, form that we need. Okay, the limit as n goes to infinity is sum from k equals 1 to n of some function of x sub k, delta x. This becomes an integral, and we already figured out a and b are 4 and 12 respectively, so it's the integral from 4 to 12. The delta x becomes the dx. The x sub k is just replaced by x. So the function now is f of x equals 6 minus the absolute value of 3x minus 12. Close your absolute value. And that is, we're integrating that function from 4 to 12. So we also know about integrating functions, what it means geometrically. Geometrically, that means that, at least as long as this is above the x-axis, we're talking about an area below this curve and above the x-axis on the interval from 4 to 12, x equals 4 to x equals 12. So let's graph that. So just take out a piece of graph paper, graph this by hand or with a graphing calculator or with a computer, and we get a shape like this. It's an upside down V shape. It's an angle. And we're looking at the area below that graph from x equals 4 to x equals 12. That's exactly this purple shaded region. So we want to find the area of that purple shaded region. Well, what shape is that? Turns out that's a nice basic shape. That's just a triangle, or the interior of a triangle, and so we want to find its area. So, what do we have so far? We have this limit of this sum is this integral, and that integral is this area, which is the area of a triangle, which is 1/2 base times height. So 1/2. The base goes from 4 to 12, so that's 12 minus 4 is 8 for the base. And the height, you can see here, goes up right here at 8, is f of 8, which is actually 6. Try that out. Let's plug it in here and see what happens. If you plug in an 8 for x, 8 divided by the 2 is 4. Right? 4 times the 3 is 12. 12 minus 12 is 0. Absolute value is 0, 0. 6 minus 0 is 6. So that tallest point right there is at 8, 6. And so the height is 6. 1/2 times 8 times 6. Let's see, half of 8 is 4. 4 times 6 is 24. And so that area, which is that integral, which is that limit of that sum, is actually 24. The next one is very similar. This time I give you this sum and ask you to rewrite it as an integral. Then using that, the fact that it's an integral, and the fact that it has some sort of nice basic shape, see if you can figure out what that final answer is for this limit of the sum, which is the value of the integral. Okay? Use the last problem as kind of a model and see if you can go through and work this one out. Press pause now. Okay, now that you're back, hopefully you've worked through this by yourself, and let's take a look and see what you might have come up with. So the first thing we're looking for is delta x. Delta x is b minus a over n. So we're looking for something that looks like a constant over n here as a factor. And sure enough, we've got 4 over n right there times this guy here. So 4 over n is going to be our delta x, which is b minus a over n. So the n's cancel here if you want to put these equal to each other, and we see that b minus a is just 4, or b is a plus 4. So what is x sub k? It's a plus k delta x, which is a plus 4k over n. So we're looking for a plus 4k over n. I believe if you look right here inside this parentheses, you'll see a is negative 2, and then it's plus the 4k over n. Okay, so that's going to be our x sub k. So, let's see, a was negative 2 then. And of course, negative 2 then plus 4 would be positive 2 for b. Okay. And if we substitute these things in, let's see what we come up with. So, here's our original. We replace 4 over n by delta x, and we replace 4k over n minus 2 by x sub k. So now we see that the delta x becomes the dx, and the x sub k becomes the x when we do our limit, as n goes to infinity, and this Greek sum, the sigma, is replaced by the long skinny s for the sum, or integral, definite integral, in the continuous case. So this turns out to be the definite integral from negative 2 to 2 of 5 plus 4 minus the square root of x dx. Now, how can we find that? Well, it turns out this is actually a quite nice shape. So if we graph this function from negative 2 to 2, what we end up with is getting a semicircle. So from negative 2 to 2, this thing comes up and it comes back down. Okay? And those endpoints where it's sort of the endpoints of that circle there, semicircle, are negative 2, 5, and 2, 5. Kind of check that out. Plus or minus 2 when you square it is 4. 4 minus 4 is 0. Square root of 0 is 0. 0 plus 5 is 5. And we get that. And if you look at this shape, kind of like a Norman window, what we get is we get the part down here, which is a rectangle, which is just 4 across and 5 tall. So it's a 4 by 5 rectangle, or a 5 by 4 rectangle, whichever way you call that. And then you got this area of a semicircle on top. Now in our previous video, we just derived the formula for an area of a circle, which you should already know is pi r squared. But we have half of one of those, so it's 1/2 pi r squared, right here, plus the area of the rectangle, which is just base times height, or 4 times 5. So 4 times 5 is 20. 1/2 of one of these 2's cancels, leaving the other 2 times pi. So it's 20 plus 2 pi is the area of that particular shape. Okay, so hopefully those examples will help us a bit with this problem.